Okay. So let's see. So I'd like to discuss quantization of the two-dimensional worldsheet, and then I'll show you that this gives rise to the critical dimension 26 in the case of the string. It will be 10 dimension for superstring setting. And so let's see. Let's see. So the action we are considering for the worksheet in the framework of Fourier formulation is this form. We can also use Nambu-Goto action, which is equivalence, produced classically. But the Fourier way of doing this, the worksheet action is of this form. And if you use equation for motion for the two-dimensional metric, so you can think of this as 2D metric. Then S becomes the Nambu-Goto action. So this is the Fourier function. Okay, and so we can define the energy, stress energy tensors. TAB is the symmetric 2x2 matrix, so it's symmetric. And then in this case, the trace is 0, which corresponds to the fact that this theory is conformally invariant. I'll tell you more about this if I have time later today. Okay, so we can use, for example, the right cone coordinate in 2 dimensions. So in 2 dimensions, the metric is of this form. And we can diagonalize it. So in appropriate framework, you can, in appropriate choice of coordinate, we can choose this diagonal metric, or you can choose this metric, where x of plus minus is equal to x naught plus minus. So in this coordinate, this condition becomes a condition that only t plus plus and t minus minus are non-zero. So in 2 dimensions, if you have symmetric matrix, you have 3 independent components. This removes 1 component, which is equivalent to say that t of plus minus is equal to 0 in this code. Okay, and if I use it for this particular action, for the Fourier coaction, this t plus plus is 1 over alpha prime of del plus x squared, and p minus minus is del minus x squared. Okay, so these are the conditions. So what we did classically was consider solution to this equation motion, which is of this form, that box of x is equal to 0 in 2 dimensions. And then subject to the condition that the energy momentum tensor vanishes. Okay. So now today we'd like to solve this equation by quantizing this 2-dimensional coordinate and see what happens. Okay. So the canonical consideration. So this was classical. This side was classical. So in quantum side. So first of all, if you perform the canonical commutation relation, and if I choose this coordinate, it's a diagonalized form of the coordinate, then the commutation relation. Oh, so I was using sigma, I guess, for the coordinate. So I apologize for the change of notation. Sigma for 2-dimensional coordinate. And so this is equal time commutation relation. This is 1, this is prime, this is 1. I'm sorry for my handwriting. So this is equal to 2 pi alpha prime I eta mu nu delta of sigma 1 minus sigma 1 prime. Okay, so this is very simple. So you might have seen it in your introductory course of quantum field theory. So this is a massless free field theory in 2 dimensions. So we can expand it in terms of normal mode. So there is a 0 mode piece, and you have this piece, and then you have negotiate a piece, and I have put 1 over n so that the commutation relation between alphas takes this form. And this will be convenient for various calculations. So n mu delta n plus n 0, and similarly for commutations of alpha tildes. And then they are Hermitian conjugate to each other, which means that this is equal to alpha minus mu, and alpha is tilde mu that is alpha minus. So you have you have this commutation relation. So the Hilbert space is generated by these spaces that we have alpha minus n1, mu1, to alpha minus n, mu n, alpha tilde minus n1, mu1, alpha minus m, mu m, on the vacuum state with momentum p. Okay, so where these n goes from n and m goes from 1, 0 to infinity, and mi and ni are all non-negative, positive, because basically the n alpha, you can, because of this commutation relation, you can think of alpha n with n positive to be annihilation operator, alpha n with negative n to be creation operator by this commutation relation. So we'll start with a vacuum which are annihilated by all the alpha with positive n and all the alpha tilde n with positive n, and then create oscillation. So you can think of these, each of these as creating new oscillation of the spring. And then the P is the center of mass for this one. So you have. So this is this. So basically the normalizable combination of this basis makes the Hilbert space. Okay, so we'll consider this as the Hilbert space. And so then what we need to do is to consider this Hilbert space and impose a quantum version of the constraint that this energy momentum tensor vanishes. Namely, that we impose the quantum version of t minus minus and t plus plus is equal to 0. Now, how to do that is a subtle story which will take us to the 26th dimension today. Okay, so let's discuss that. So first, let us look at this, what this energy momentum tensor look like in this canonical quantized form. So, so T, let's write for simplicity T to be T plus plus. This is a right mover. So this is a left move, I suppose. Right? So this is 1 over alpha prime the plus of x squared. Now, x has this harmonic oscillator expansion, and this has Fourier mode. So t is basically the square of the derivative of this fellow. And so this one also has a harmonic oscillator expansion, of Fourier expansion. So minus infinity to plus infinity of Ln e to the minus I n sigma plus. And we can easily find, by substituting these alphas, we can easily find Ln to be equal to the convention over n of 1/2 of alpha n minus n, alpha n. And these are constructed by the target space method, like this. Okay? And similar for t minus minus. And basically for t minus minus, we just replace all the alpha by alpha 2. Okay. And okay, and then I would also extend this to define alpha 0 to be alpha 0 tilde to be equal to square root of alpha prime over p nu. So this will be so I guess here m can be 0. So I would define it in this way so that the formula works out correctly. Okay. So this seems to be okay, except that there is an ambiguity. However, L0 is problematic because so for Mn with n non-zero, this gives you a good definition of operator acting on this Hilbert space. Okay, because if n is non-zero, then you have so if you look at this term, you have alpha n minus m mu, and if you consider commutator of this, well, according to this commutation relation, this has non-zero commutation relation only when n plus m is equal to 0. And so that means that this plus this has to be 0 in order for this to be non-zero. So if n is non-zero, then this has to be equal to 0, right? Because m and minus m cancels. So that means that it doesn't matter whether the ordering of these two operators is irrelevant. We can order it either way. And so then the action of Ln on this Hilbert space, so let's call this a Hilbert space, H is well defined. Right? I hope it's clear because what this means is that you just act on this. Of course, there are infinite many terms, but actually when acting on this Hilbert space, this action is truncated because, so let's take some element of the Hilbert space. And suppose for simplicity that such elements can be expressed as finite linear combination of these fellows. Okay? So if psi is the element of the Hilbert space, which can be expressed as finite linear combination of these, so that means that for sufficiently large n, so maybe I'm in math department, so I should say it more mathematically. So there is some n which is positive, such that alpha n mu psi is equal to 0, alpha n tilde mu psi is equal to 0 for n greater than or equal to n. Okay? So this is easy to see because psi is a finite linear combination of these bases. Each basis element is created by acting a creation operator on the vacuum. So for each one of these elements, there are a finite number of creation operators. If you have finite linear combination of these, then these are created by finite number of creation operators. So if I take capital N to be much bigger than any one of the n's for this creation operator, then we can such state should be annihilated by this. Right. So now let's look at this one. Let's look at this one. Okay, so let's look at this one. So n is summed over minus infinity to plus infinity. If m is positive, this, and if m is greater than capital N, so what this means is that if I consider alpha n minus m alpha m, if m is greater than or equal to n, then this would annihilate. C annihilate. Right? And moreover, if n minus m is positive, is greater than n, then this also annihilates some. Because now this one annihilates. I already argued that ordering does not matter. So we can, if m is greater than n, we can first annihilate the state by acting this one. If n minus m is greater than n, then we first act this on the state and annihilate. Right? So that means that either if m is greater than n or greater than n minus m is greater than n, this one is annihilated. So the only situation when m does not annihilate, this does not annihilate the state is, so psi is not annihilated when m is less than of capital N, but is greater than n minus capital M. Okay, so capital N is fixed for psi. Small n is fixed by the definition of this operator. So for given Ln and for given psi, there is always only finite range of m, which does not annihilate the state. So therefore, the action of this operator on the psi is well defined. Okay, you understand? Okay, so that's good. So I try to show this precisely. So this operator, what I'm saying that this operator is well defined on this pupils. Okay, so that's good for Ln. But so I say that this is good when n is non-zero, but when n is zero, but it's problematic when n is equal to 0, because you have L0, which according to this definition is minus m alpha m mu mu. However, alpha m alpha minus m mu is actually non-zero by definition of commutation relation. So now the ordering matters. Whether this is this side or this side matters. Fortunately, that ambiguity is a constant shift. Because what this means is that if you compare this and this, by this commutation relation, what it means is that they only differ by constant. So that means that if you have different convention of how you order this, that this convention differ only by constant. If you don't make a reasonable choice, the difference between two different conventions can be infinite. So that program, so one has to make a definition, choose a definition of L0 so that its action on the Hilbert space is well defined. And among the choice of L0 for which the definition of the Hilbert space is well defined, the difference is just constant. So for now, let's parameterize this ambiguity by just introducing a new constant. So, so what it means is that we define, so therefore we define L0 to be somewhat arbitrary by declaring that we choose always to be negative n to be the first one and positive n to be the second one. And then there's the zero mode piece. Okay. Where alpha 0 mean is defined to be like that. So so this is called the normal ordering. So this is a sort of typical ordering that is employed in quantizing defining bilinear operator in the free field theory. So this is a definition where the vacuum state in the harmonic oscillator gets annihilated. Because annihilation operator always comes to that. So this is a normal ordering convention. This is just a matter of convention. So I'm not saying that this is a unique choice. And in fact, we'll see that the constant shift is actually needed. So the reasonable definition. So the reasonable definition will to impose the condition that the limit of tends to 0 to be Ln minus A of delta n0 is equal to 0, where A is some constant. Okay, so Ln is the Fourier coefficient of Ln. So if we want to impose L plus plus to be 0, we would impose a condition that Ln to be annihilated. However, there's a constant shift ambiguity in L0. So I'm going to introduce this Kronecker delta so that the constant part can be shifted. So this will be a reasonable condition, except that so there's one more twist, which is that this condition cannot be consistently imposed on the Hilbert space. So this is another typical thing that happens in quantum field theory. So what happens is the following. So because the definition of Ln, now we define Ln to be the normal order operator. So where normal ordering of alpha means that alpha with the creation operator to the left. To the left, annihilation to right. Okay, so this was the definition. But if you use this as a definition of Ln, then we'll find that if you actually calculate commutation relation of Ln, then it takes this form. So actually, I will show you the calculation later, either today or next time, where C is a dimension of the target spacetime. Okay, so this makes it difficult to impose this condition. This makes it difficult to impose this condition. The reason is that this is not. So here today I'm just going to claim that commutation relation of Ln for this operator. So see, we know the commutation relation of alpha. So therefore, commutation relation of Ln is well defined. So if you do the calculation, you'll find this. And I'm just declaring it now. I'll show you how to do it later. But I just want to point out that if this is a commutation relation, then this condition is not compatible with this condition. The reason is not compatible with Ln minus A and Z is equal to 0. And the reason is that if you calculate, say, commutation relation of n with m is equal to minus m, and this is equal to 2m m0. But then this is equal to 12c n cubed minus n delta n plus n 0. And it's programmatic because the coefficient here and the coefficient here has different n dependence. Different n dependence. For example, if this cube part was 0, then we could have consistently imposed this condition on this. Because the reason is that, well, if you impose this condition, the left-hand side will be 0. Left-hand side 0 because, well, you have to shift by constant, but constant commute with everything by definition. So if you impose this condition, if Ln minus A delta N0 is imposed, the left-hand side is equal to 0 because these are these branches, right? The right-hand side, well, if you substitute L0 to be this, then the right-hand side, okay, we don't need this one because the n plus n. So the right-hand side, we're going to replace L by A. So right-hand side becomes 2NA plus 12E n cubed minus n is equal to 0. Okay. So this is problematic. If this n cubed part is non-zero, then we could have defined A to be C over 24 to satisfy this condition. But since there is n cubed part, so it's not possible to impose this condition for all n. So this is a contradiction. So we cannot impose this condition. This is not very surprising, and in fact, this happens in quantum field theory all the time. That there often happens the situation where you want to gauge some symmetry. Here we are trying to sort of. So we showed you a few maybe last lecture. These conditions is a reflection of the fact that we have reparameterization invariance on the two-dimensional worksheet. And if we have that kind of gauge symmetry, we would need to impose this condition. And then you find that this condition cannot be imposed as operator relation on the Hilbert space. So for example, this thing also happens in quantum electrodynamics, the consideration of the Maxwell set. What we do, so quantum version of what we do is to not to impose this as operator relation, but impose this as for the expectation values and matrix element between Hilbert spaces. So that means that we would impose the condition. Instead, we would impose the condition. So the quantum version of the constraint is that there is a subset of the Hilbert space or physical Hilbert space, which consists of some physical state. And for any two physical states, this condition is satisfied as for the matrix set. Okay, so instead of imposing this as operator relation, we will impose this for the matrix elements between any pair of qubits, physical state. Okay, so that's what we will impose. And so one way to impose these conditions, which we're going to employ, is a condition. So we can, for example, impose. In order to satisfy this, we can require that Fn minus A of n0 annihilate any element of the physical Hilbert space when n is greater than or equal to 0. So if we impose these conditions, then this is satisfied. So therefore, for for calculation of physical quantity, this condition is satisfied. Okay, so this is the approach we take to do the gauge fixing, and this is actually a very standard approach. If you have taken introductory quantum physics theory course, you might have seen that this is the condition that they use. And another requirement that we will impose is that two states that are related to each other under the action of elements are equivalent. That is to say that if you have two physical states which are related to each other by a shift of the action of Ln for n greater than 0, then we regard to be physically equivalent. So that we regard this namely as describing the same physical state. The reason that we have to do it is that this only takes care of the half of the constraint. We would like to impose this for both n positive and negative. And so for the negative part, this is the correct approach. And so I don't have time to explain why this is the approach that is required by physics, but this is what you should have learned in introductory course of quantum physics theory. One thing I would like to point out that this is very similar in spirit in what mathematicians consider in cohomology. So namely that, so in mathematics, what people consider cohomology, what they do is that they consider some kind of operator which is, for example, the simplest case is some operator which is nilpotent. That is that if you add that operator twice, the Hilbert state get annihilated. And you consider all the states which are annihilated by that operator modulo the shift by states that are created by that operator. It's also called cohomology. And so you can think of his physical state as a cohomology with respect to the action of this alien operator, which are called the Virasoro operators. And these are called Virasoro constraints. Okay. So, yes, please.
Is this the same thing conceptually for the optimization in the...
Yes. Well, so this is a very important point. So yes, yeah. So what I'm going to do next is to require that the result of space of solution to these equations are independent of choice of gauge fixing condition. And that leads to the 26 dimensions. So when you can do this consistently, then this is equivalent to the Faddeev procedure. So actually, if I have time, I will explain them. Okay. Okay, so now the next task is then to solve this condition. So let's try to solve this condition. So before going into this condition, solving this constraint, let me actually make comment related to the question being asked. So, so the reason we are considering this condition, T plus plus is equal to 0, T minus minus is equal to 0, comes from the gauge symmetry. So in the case of, in our case, this is a reparameterization of the 2D worldsheet. So we have the sigma A, so you can map this to another. So we wanted to, we found that the theory should be invariant and a change of the two-dimensional, invariant and the way you parameterize the two-dimensional worldsheet. And that leads to the gauge symmetry and that leads to the function. Okay, so now, in the classical analysis of this system that I discussed in the first couple of lectures, I pointed out that there are actually two equivalent ways to deal with this gauge symmetry. So one was the light quantity, light component gauge symmetry. Light on gauge. So this was the first condition that we considered, which is a condition that we separated x mu, where mu goes from 0, 1 to b minus 1, into the two things. So we separated this so that, well, I guess I need to remember which combination L0 I take. But for example, I can take L plus minus to be x0 plus and minus xd minus 1. And then the rest xi, where I goes from 1 to d minus 2. Okay, so these are target space coordinates. And then, but we can choose, we can fix the gauge. We can make use of this freedom to choose the coordinate on the worldsheet. We can impose the condition that x plus is proportional to sigma 0. That we want to say that this is a time on the worldsheet. We measure the time on the worldsheet by this condition. With this choice, we can solve this equation. Can be solved. And then we find that x minus is given by x plus and xi. So this is determined. So therefore, what light cone gauge does is basically remove x plus and x minus from physical degrees of freedom. These are totally fixed by the gauge condition. So that means that these are the only degrees of freedom. So namely that the oscillation of string is only in this d minus 2 dimension. String oscillate only this d minus 1 transverse direction. This is actually geometrically very clear that we can do this because so I explained it last time. For example, suppose you have this worldsheet. So this looks like this is not oscillating at all. But if we choose like the very wavy worldsheet coordinate, it looks like it's oscillating. So it's clear that in string oscillating in this direction along the propagation, then it should not count as an oscillation. So this oscillation in x plus and x minus directions are one of those things. So therefore, we can remove these as unphysical oscillation. So in light cone gauge, therefore, we see that oscillation is only in d minus 2 dimension. And in d minus 2 dimension, we have this harmonic oscillator. So therefore, the physical states satisfying these conditions are easy to solve. So therefore, in light cone gauge, the physical states are So basically created by excitations in this n-1 transverse direction. Acting on the vacuum with fixed moment. So this is a condition. Now, so let's compare this with the other gauge fixing condition that we are considering, which is called conformal case. Where we try to sort of respect the Lorentz invariance in the target space. Here, we are choosing these two coordinates as sort of special directions and imposing these right-hand gauge conditions. So this breaks the Lorentz invariance of the target space. That we find if gauge symmetry can be consistently imposed, because if you want to rotate the target space coordinate by Lorentz boost, for example, we could impose these conditions for the new coordinate. And if the cell is gauge invariant, these two descriptions should be the same. They should give the same physical description, provided the gauge conditions, gauge symmetry is consistent. Similarly, if gauge symmetry is consistent, then it should not matter which gauge condition we impose. We can impose another gauge condition, conformal gauge. So conformal gauge condition, what we do is don't choose particular direction in target space, just impose this condition, which is to say that just impose this condition that n minus a of delta n 0 annihilate the vacuum physical state of n non-negative, and then we want to say that two physical states are equivalent modulo n minus n. Okay. So this is a conformal case. So you consider physical state satisfying this condition. Okay. If gauge symmetry is consistent, that is that in the language of quantum field theory, if there were no anomaly, then these two should give rise to the same Hilbert space. That one state in Hilbert space is equivalent to the other state in Hilbert space. Now, that's not obvious. That's not obvious because these are totally different conditions. Here, the solution to this gauge condition is that it's an oscillation d minus 2 dimension. This in principle has d-dimensional oscillation because these are created by a state with alpha minus n mu, where mu goes from 0 to d minus 1. Okay? So let's see when and how they become equivalent. Okay? So that's what we want to do. So let's look at what these conditions are. Okay? So first, let's look at the condition L0 minus, so for n equals 0, we have L0 minus A to be equal to 0. Now, so what's L0? Well, L0 is equal to 1/2 of summation n of normal ordering of alpha minus m alpha n. So this is equal to summation m is 1 to infinity alpha minus m alpha n plus 1/2 of alpha 0 squared. The alpha 0 squared is equal to a quarter of alpha prime e squared. Okay, so now let's look at what these are. Okay, so alpha is a harmonic oscillator. This is an annihilation operator, this is a creation operator. So just like you learn in harmonic oscillator, so for example, in the harmonic oscillator that we look at in in the class of quantum mechanics in undergraduate, we see that A dagger A is a number operator, right? That is, it's count how many oscillations. So these are integers. Now alpha is normalized slightly differently because we normalize this to be n times delta n plus n. So these are integers. These are integers. And this is a momentum. Right? So these are integers, so let's call this as n. But I define this to be capital N. So then if we impose a condition that L0 minus A of physical state to be equal to 0, well, what this equation means? Well, this equation means that n plus force of alpha prime p square minus A is equal to 0. P is a momentum. P is a momentum. So minus p square, therefore, is equal to alpha prime minus p square is equal to alpha prime over force of let's see. Yes, oh, okay, of n minus A. Okay. Okay, so what is this? Well, so P is a momentum, right? And I'm choosing the almost minus convention. So that means that this is equal to P0 square minus P vector square, so it's a space momentum. So that means that this is mass square for the state. So the mass square of this physical state is equal to alpha prime over 4 n minus n. Okay? This is what this means. So let me write. So this is important. So let me write it. So let's define this to be n. So then the mass square is equal to 4 over alpha prime n minus n. Okay? So n is the non-negative integer. Count the number of excitations of the string, basically. And so if n starts with 0, that is the ground state of oscillation. So the ground state has mass square is equal to minus alpha prime for A. And for n equal to 1, you have mass square is equal to alpha prime over 4 n minus A. It's 0. Okay? Or 1 minus A. It's 0. So you have this. So basically determining this constant dictates what's the mass square of the particular excited state. Okay? We'll find that in the case of bosonic strings that we are considering, that the string theory whose degrees of freedom is only this bosonic coordinate in the target space, then actually in the next stage we will find that A is actually 1 in this convention. So that's problematic. That's problematic because in that case, that means that the ground state, which is a physical state, has mass square negative. It's a tachyonic state. So that is such a theory is pathological for various things. First of all, the physical state contains tachyon, which propagates faster than the speed of light, causing all sorts of causality questions. Like you can go back to the history and kill your parents or things like that. So that's problematic. Another way to say it is that such a theory is unstable. Because the state with mass negative mass square means that if you try to write it in field theory, it has a potential which is not bounded from below. So you can actually the original the vacuum state you are considering was not stable vacuum, and there must be some more stable vacuum elsewhere which we need to find. Okay, so the bosonic string we will find is actually pathological for that reason. This problem will be avoided in superstring theory that we'll consider later. And that's one of the motivations for considering superstring theory, to actually remove this pathological state. In fact, there are situations in bosonic string where we understand the nature of this instability and find stable vacuum where this instability mode eventually roll down. But that we'll discuss later if I have time. So I just want to point out that what will be coming later, which is that I'm going to determine A to be equal to 1. Okay, so let's see how okay, so I need to tell you how this is determined. So this is determined by looking at the first excited state. Okay, so let's look at the first excited state. So let's look at n equal 1. I'm so happy that I brought this Hagromer chalk. It's much better than the previous one. So n equal 1. So what kind of state can we have for n equal 1? Well, so if I have alpha n acting on the vacuum, then this would have n is equal to n. Because the computational relation was like that. Okay, so compared to the standard harmonic oscillator, alpha n is normalized like square root of n times am, for example. So capital N takes into account this n factor. So that means that for n equal 1, we should consider alpha 1. Okay, so therefore n equal 1 state is a linear combination of these pairs. It's a vector. The first excited state of this string is a vector. So we can introduce some polarization vector, which depends on momentum. So E mu P is a polarization of the n equal 1 excitation. Okay, so let's see what these conditions imposes for polarization. Well, first of all, we impose this condition. Let's call this as the physical state. Let's impose these conditions. So this gives rise to the condition that the mass square, so namely that minus p square, which is mass square, is alpha prime over 4 and a minus 1. Huh? Oh, no, minus 1 minus a. Okay, so that's one thing we see. And the next thing we see is that we need to impose L1 acting on the physical state to be 0. Well, so what does this condition mean? Well, L1, Ln, remind you, is a summation of alpha n minus m, alpha n. Okay, but we are acting this on alpha minus 1 acting on the vacuum. So that means that if m is greater than 1, then it's automatically annihilated. So m has to be less than 1, less than or equal to 1. But we also have to we are imposing L1 to be annihilated. So that means that if m1 minus m is again greater than 1, then this would annihilate. So the only choice is m equals 0 or 1, right? So in either case, this condition is equivalent to the condition that alpha zero mu alpha 1 mu annihilates the physical state. Right? Because all other term vanishes. So the only non-zero condition is this condition. So therefore, L1 physical is equivalent to say that alpha 1, alpha 0 acting on the physical state is equal to 0. But P, alpha 0 is momentum. Alpha 0 is a momentum by definition. I wrote it, maybe I have erased it, but alpha 0 is a momentum. So that means that this, and the alpha 1 and commute with this one. So that means that this condition is equivalent to the condition that P mu, E mu is equal to 0. Namely that polarization vector is orthogonal to the direction of the momentum. Okay. So now final condition, which is to say that we try to identify two physical states which are related to each other by the action of some state with a Virasoro action. But since we are comparing first excited state, we only consider L minus. Okay, so what kind of state do we have over here? Well, so we are considering n equals 0 state. So we are acting this on this. So the only state with capital N is equal to 0, namely one oscillation, can be obtained when this is a vacuum state. So we consider L minus 1 acting on the vacuum. Okay, so L minus 1 is equal to some 1/2 of summation of n alpha minus 1 minus n alpha n. But since this is vacuum, so when if n is greater than 1, equal to 1 or greater, then it's annihilated. It's also annihilated if n is less than 0. So the only possibility is the case when n equals 0 or minus 1. So either case, this would give rise to P mu alpha minus 1 mu acting on the vacuum. So that means that this condition is equivalent to the condition that E mu gets identified with this for some constant. Okay. So now let's look at this one. So let's try to count the number of polarization. Okay. So initially we have E mu, so that it has a D polarization, right? Because mu goes from 0 to D. And we are imposing this condition for the B square, which does not change the number of polarization. We impose this condition. So that is a one linear condition for D component. So it removes one component. So this gets you to the D minus 1 polarization. If we can impose this additional condition, then you will remove yet another condition, right? So that would give you D minus 2 polarization. And so we'll be happy because I said that in Dipole consideration, there are D minus 2 polarizations, there are D minus 2 direction of the excitation. So that will be consistent. Except that we need to make sure that this condition can be imposed. And it's not obvious that this condition can be imposed because the state that you obtain by shifted by P should also satisfy this condition in order for this to be removed. Because compatibility requires that both this state and this state should satisfy this condition. So therefore, in order for this to remove one more state, this requires this condition requires P, this to satisfy this condition, which means that P square is equal to 0. So only when P square is equal to 0, then this removes one more state, and then you get a result which is consistent with right conservation. But in general, mass square at this level is not 0. It's proportional to 1 minus A. So this leads to the a statement that if you demand that this conformal gauge quantization of the worksheet to be consistent with right gauge quantization result, A has to be fixed to be 1. So A is 1, so ground state is tachyon. So that's the consequence. So let me state it. So here, so the right quantization would say that the first excited state would be of this form, where I is equal to 1 to D minus 2. Whereas the conformal gauge would say that the ground state, the first excited state is of this form, where mu goes from 0 to D. But subject to the condition that this is equal to 0 and E mu goes to E mu plus T mu lambda, and then P square is equal to alpha prime for A minus 1. Now, so therefore, the consistency requires A is equal to 1. Because if A is not equal to 1, this does not remove a condition. This equivalence condition cannot be imposed consistently with this condition. And so therefore, there is a discrepancy between the number of divisors. So if we require that conformal symmetry to be the repenetration can be gauge fixed consistently in any gauge condition, then A has to be equal to. Okay. There is another way to see why this is required, and that related to the Faraday-Popov story that somebody asked. If I have time, I will discuss that. Okay, so this is the excitation in N equal 1. So now you can ask, well, so now N equal 1 excitation demanded 1 consistency condition. If you go to the next excitation, do we get more conditions, or once this is cleared, all the excitation become consistent? We'll see that N equal 2 excitation gives you yet another condition. So let's look at why this is the case. So let's look at N equal 2. So what kind of states should we consider for the second excited state? There are two candidates. One is, so I said that this will give you 1 excitation. So if you want to have level 2 excitation, one possibility is to excite the ground state, the vacuum state, by Hartree A minus 1 operator twice. So now it's a tensor. It's a tensor. So I introduce tensor polarization. Another possibility is, well, you also have alpha minus 2 states. So we can have a vector polarization. So therefore, the second excited states are a tensor, the linear combination tensor and the vector. Now, so we also need to impose a condition that L0 minus, now we know N equals 1. So I write L0 minus 1, the physical state, to be equal to that. And that requires a condition that P square minus P square is equal to plus 4 over alpha prime. So now this is a massive state. Massive particle. So the second excited state, so ground state was tachyon. The first excited state is a massless vector field. And the second excited state is the massless tensor and the vector, linear combination of them. Okay. So how many states do we have? How many states do we have? So okay, so how many states do we have? Well, we have tensor, and this is symmetric because these creation operator compute with each other. So that means that E mu nu is E nu mu. So linearly independent component has to be half of D plus 1. Right? And E mu has D component. So if before we impose any conditions, the number of degrees of freedom was the second excited state is the sum of these two numbers. Okay. Now, so how many conditions that L1 is equal to 0 and L2 equal to 0 to be imposed? Well, so if you impose these conditions, then you will find that there are D plus 1 conditions. This gives rise to D plus 1 conditions. Okay, so how do we see that there are D plus 1 conditions? So let's look at E mu nu. So L1 is summation 1/2 of 1 minus n alpha n. Okay, so if you act this on this, then so if m is 1, then you can replace this. If m is 1, this becomes like that. So L1 is equal to 0 on this will give rise to P mu E mu nu is equal to Z. Okay, so L2 is equal to 1/2 of summation n alpha 2 minus n alpha n. But this does not impose any condition on this. Because if m is equal to 1, this is 1. So there are, it imposes two conditions. I'm sorry. It imposes one condition because this would impose a condition that E mu nu is equal to 0. Right? So let's see, is this right? So because it contains a term like alpha 1 mu, alpha 1 mu. So this will impose this condition. So let me see. Let me make sure I'm not making a mistake. Right. Right. So that's let's see. Oh. Yes. Oh, I'm sorry. So we should consider this linear combinations. So we should not impose this separate. Yeah, so I miscounted. So yeah, so I was confused. So we should impose this condition. So we should consider this linear combination. We should consider this condition, and then on this we impose a condition that L2 and L1 is equal to 0. Okay, so let's first consider L2. So L2 is a linear combination of L2 minus M, alpha 2 minus M, alpha M. So let's look at the relevant term. So this contains in particular alpha 1. So if M equal 1, you have alpha 1, and then there's another relevant term is alpha 0, alpha 2. Right? Yeah, so these are the only two terms that are relevant for this, because another one is alpha minus 1 and 3, so that will not count. Okay, so if you impose F2 equals 0 on this condition, then this would turn this into E mu mu. And then this would impose P mu E mu equals 0. Okay, so this is one condition. Another condition is L1, which is the one half of alpha 1 minus M, alpha M, which is equal to alpha 1, alpha 0, alpha 1. And there are two terms. And there's another term, which is alpha minus 1, alpha 2. Okay, so so these are the two terms that are relevant. There are other terms, but the other terms trivially are not. Okay, so let's look at one. So this one acts on this and replace one of them to be constant. And you have momentum, so that means that this is equal to 0 to impose the condition that P mu E mu nu. Okay, and then this will replace alpha to be alpha minus 1, so that would mean that E mu. So this would impose this type of. So you have, let's count the number of conditions. So you have one condition and you have D condition. Okay, good. So you have, that's why I wrote you have D plus 1 conditions. Okay, so you have D plus 1 conditions. So that means that you remove, so you have this many states, you impose this many conditions. So how many states do we have left? So let's write it over here. So you have 1/2 of D plus 1 plus D minus D plus 1. And so let me write it square plus 1/2 of D minus 1. So this is a state you obtain by imposing these two conditions. Okay, so on the other hand, let's count the number of states in light cone. So the light cone, in the light cone configuration, we have similar kind of state, but now the polarization is only in these transverse directions, which means that we have alpha minus 1 I, alpha minus 1 J, or alpha minus 2 over I, where I and J goes from 1 to D minus 2. So that means that number of states is D minus 1, D minus 2, plus D minus 2, because these are this many components and there are this many components. So that means that 1/2 of D squared minus D minus 1. Okay, they don't agree, but it's not surprising because we still have to impose in the conformal case, the condition that the two physical states are equivalent modulo L minus 1 acting on something and L minus 2 acting on something. Right? Okay. So what kind of state do we get? Well, from this, you get the state like L minus 1 alpha minus 1 mu acting on the vacuum with momentum P. And you have some polarization vector, so we can have, so what kind of character should we use? E tilde of mu or something like that. So you have another polarization state. And then you have, so this state would give rise to another state, right? So you have L minus 1, L minus 2. Yeah. Okay, so and then there's also some linear combination. Yeah, you can also have this state here. Okay. So so this would almost work. This would almost work. And the reason for that is that the number of states we would like to obtain by remove from this by imposing this equivalence relation is a difference between that number and this number. So let's count the number. So in conformal case, we have half of d squared plus half of d minus 1. And in right-cone gauge, we had 1/2 of d squared minus 1/2 of d minus 1. Okay. So that means that you want to remove this state. You want to remove this state. Okay. Now, look like we can almost remove this state just by using this thing. Right? But it doesn't quite work that way because this itself should satisfy the conformal gauge condition. So we need to require that this state satisfies L2 of E mu tilde L minus 1 alpha minus 1 mu is equal to 0. So that would require P mu E tilde mu to be equal to 0. So therefore, this would account only for 1 degree of freedom, d minus 1 degree of freedom. So that means that this combination should also remove one more state. But this would require that this satisfies the physical condition, physical state condition. So let's finally check to see whether this is satisfied. So we would require, we need L minus 2 plus some constant. So let's call this constant to be gamma of L minus 1 squared acting on the vacuum state to satisfy L1 and L2 is equal to 0. Okay, minus. Okay, so let's check the condition. So let's first require the condition that L1, L minus 2 plus gamma of L minus 1 squared equals 0 is satisfied. So we can use commutation relation. So we're going to use the commutation relation that let me write the commutation relation here. That Ln is equal to n minus m, Ln plus n, So 12b n cubed minus n delta n plus m. So we're going to use this computation relation. So first, let's compute the computation relation of this and this. So this would give rise to, so here this term is not relevant because 1 and minus 2 do not cancel with each other. So this will just give you 3n minus 1. And then we can consider commutator of this with this. So there are two possibilities. So there are two L's. So first of all, since n equals 1, so this term does not contribute. So there are two possibilities. So you have 2 gamma L0, L minus 1, or 2 gamma of L minus 1, L0, acting on the vacuum state. So by definition of the physical vacuum state, L0 is equal to 1 on the physical vacuum state. So we by taking that into account, we can easily calculate this to be 3 minus 2 gamma acting on L minus 1 of the vacuum. And so this is being equal to 0 to require that we choose gamma to be 3 half. So we could have considered any linear combination of these, but gamma is chosen to be minus 3 half by imposing this condition. We also need to check whether this is satisfied. And this is again simple exercise of algebra. So we use this algebra and the condition that L with positive n annihilate the vacuum state. And so let's first consider commutation of L2 and L2, because if L2 acts on the vacuum, it gets annihilated. So we just need to choose a commutation relation. But now that's interesting thing that commutation relation involves this term, because now n equals 2. So 2 to the cube minus 2 is not equal to 0. It's 6, so it's contribute. So it gives rise to 4L0 plus 12 over d. And 2 to the cube is 8 minus 2, so that's 6. And then we have gamma, so that gamma I already know that is 3 half. And then you have 3 times L1, L minus 1, plus 3 half of L minus 1, 3 times L1, but this annihilates the vacuum. So this annihilates the vacuum. And this one, we can now move this to the right-hand side to make it as 2L0, which we can evaluate to be 1. So by combining this, so this is 4, this is minus 4. This is 2 cancel this, so this is minus 9. And this is 6. So that means that this is equal to minus 4. And this is 6, so that means that this is half of d. And this is minus 9, acting on the vacuum. So 9 plus 4 is 13. So this is equal to d over 2 minus 13, acting on the vacuum. And consistency demands that this is equal to 0. So what this means is that this is also physical state. This is also physical state. This is also physical. Only if and only d equal 26. Okay, so this is what we wanted to show. That the consistency of the conformal gauge fixing and the right cone gauge fixing demand that this state is physical, satisfies the physical state condition, and this condition gives rise to d equal 26. So now you can derive why the bosonic string requires 26 dimensions. If I have time, we will go through this also superstring case, but in superstring case, we can also do similar exercise. Consistency of the right cone gauge condition and conformal gauge condition in the case of superstring theory also shows that in that case give rise to d equal 10. And you can phrase it in various different ways. Here, I demanded that conformal gauge condition to be equivalent to the light condition, and that gave rise to D equal 26. Alternatively, we could have also demanded light cone gauge condition to be Lorentz invariant. Because if the light cone gauge condition is equivalent to conformal gauge condition, since conformal gauge condition is manifestly Lorentz invariant in space-time, therefore light cone gauge condition should also be Lorentz invariant. Namely that we should be able to construct light cone and Lorentz transformation generator in the light cone gauge, and that to satisfy the consistent algebra. That also gives rise to 26 dimension. In fact, that was how originally 26 dimension was discovered. And there is yet another way to derive it, which is related to the Faraday-Popov gauge condition. And that is more geometrical. So if I have time, I will discuss that. But anyway, so this is the derivation of 26 dimension. Now, I have not told you what whether if you go to even higher excited state, it gives rise to yet other conditions. But so we could go on and do that, but there are more efficient ways to show it. So if I have time, I will do that. But today I just showed you that how the 26 dimension can appear. Okay, so that's it for today. Thank you. Okay, well, gamma, so we just require that, so let me first stop it.